In this second lecture, we're going to discuss the time value of money. And this is a critical component to understand how to calculate a net present value associated with a project. So one way to think about the time value of money is to simply say that a dollar today is worth more than a dollar tomorrow. But as it turns out, we can say something much more specific than that. So here we have a timeline, and you can envision us standing at time zero. And as you look, you can see that there are periods out in the future. And in this graph, they go from period 1 out through period n. And there's a flow of cash associated with each of those future periods. And they're denoted by the letter F. And there's a subscript on each one of those that denotes what period that cash flow is either going to be paid or receive. So F sub 1 would be a cash flow 1 period ahead. F sub 3 would be a cash flow 3 periods ahead. And F sub n would be a cash flow that's n periods ahead. We can talk about the amount of cash we have today as the present value of that cash. Or we could talk about the value of a future flow that we're going to receive some periods ahead. We could talk about what the present value of that is. When we do these calculations, there's going to be an interest rate that is going to govern this calculation. And for now, we're going to assume that that interest rate is the same every period. Okay? And we'll denote the interest rate by R. Now, I'm going to start out by talking about future values because I think sometimes there's more intuition associated with that. So if you wanted to know what the future value of cash that you have on hand is that you're going to, say, deposit in a bank account, the way that you would calculate what the value of that cash will be at period n is to take the cash that you're going to deposit in the bank today, the present value, and multiply that by 1 plus r raised to the nth power. So what would be an example of this? Well, suppose that there was a bank account around and the interest rate on that bank account was 10% per year. And you wanted to know what amount of money you would have in the bank at the end of 1 year if you deposited $1,000 in the bank today. And so applying that formula, what would we do? Well, what we're trying to calculate is we're trying to calculate F sub 1. So you would take the amount of money that you're depositing in the account today, $1,000, and you would multiply it by 1 plus the interest rate of 10%, which of course 10% is 0.1. And so you're taking 1,000 and you're multiplying it by 1.1. Well, what that means is at the end of the year, you would have $1,100 in the bank. Right? So you deposit $1,000 today. Over the year, you earn interest at 10% per year. And at the end of the year, you have $1,100. So that is the future value of that $1,000 a year from today when there's a bank account around that pays you at the rate of 10% per year. Now, what if you wanted to ask the question of what amount of money would you have in that same bank account if you left that money in there for 2 years? Well, in this case, we're calculating F sub 2. The 1,000 is the same. That's the amount we're depositing today. But now we're going to multiply that 1,000 by 1.1 squared, not 1.1 to the first power, because we're letting that money sit in the bank for 2 years. And you'll notice that when you do this calculation, what you'll find is that you're going to wind up with $1,210 in the bank account at the end of 2 years. So notice what happened. In the first example, right, we got interest of $100 essentially, right? And in the second year, we got interest of $110. We didn't just get $100. We got interest of $110. And that's because in the second year, not only did we get interest on the $1,000, but we got interest on the $100 in interest that we got in the first year. And people often refer to this as compound interest. So again, if you left the money in the bank for a year, you'd have $1,100. If you left the money in the bank for 2 years, you'd have $1,210. Now, these examples are all using dollars, but you can use any currency that you want to use, okay? You can do these calculations with absolutely any currency, and the examples that I'm going to use are just going to use dollars. Well, let's talk about present values because that's really what we're going to use for evaluating projects. And the formula here for the present value is just solves for what the present value is from that other formula that I showed you previously here. So all we're doing is we're putting the present value on the left-hand side and we're solving for it. And when we do that, what we find out that the present value of a future flow of cash, F sub n, is equal to that future flow of cash divided by 1 plus r raised to the nth power. So let's see an example of this. Suppose that there's an interest rate around that pays you at the rate of 10% a year, and you want to know what amount of money do you have to put in the bank today to allow you to withdraw $1,000 a year from today. So this is a different problem than we calculated before. So what we're solving for here is the present value of $1,000 a year from today, assuming there's a bank account that pays you at the rate of 10% a year. So to calculate this, what you do is you take the 1,000, which is F sub 1 in this case, because it's a year away, and you divide by 1 plus r. The r again is 10%, so you divide by 1.1, and you find out that the present value of $1,000 a year from today, when there's a bank account around that pays you at the rate of 10%, is $909.09. And you can see that if I took that $909.09 and left it in the bank and it earned 10%, at the end of the year, I would have $1,000. What's interesting here is to understand that what this calculation is basically telling you is that $1,000 a year from today is economically equivalent to $909.09 today if there's a bank account around that pays you at the rate of 10%. And the reason we say they're economically equivalent, because if you had $909.09 today and you put it in a bank account that paid 10% a year, at the end of the year you would have $1,000. So those two things are economically equivalent. The other thing that this really points out, and this is really key, is that money has a time dimension. It's not enough for me to say, I'm going to give you $5,000. That really doesn't tell you anything. You need to know when I'm going to give you the $5,000 because of the time dimension associated with money. Let's look at another example. Here we're asking the question, what amount of money would you have to put in the bank today if you wanted to be able to withdraw $1,000 2 years from today? And so the only thing that's changed here relative to the problem that we just did is now we're saying we want the $1,000 2 years from today. So in calculating the present value, we take the $1,000, which is the amount we want, but now we divide by 1 plus r to the second power because we're going to let that money sit in the bank for 2 years. And when you do this calculation, what you find out is that the present value of $1,000 2 years from today is $826.45. Another way to say that is $826.45 today is economically equivalent to $1,000 2 years from today if there's a bank account around that pays you at the rate of 10% a year. In terms of the jargon that we're establishing here, the present value of $1,000 2 years from today is $826.45. Now, you probably wouldn't be surprised if you took that $826.45 and put it in the bank for 1 year at 10%, you probably wouldn't be surprised that the amount that you would have in the bank would be $909.09. And then, of course, would you do? You'd leave that $909.09 in the bank account for another year, and it will grow to $1,000. So now let's put those two examples together. Let's suppose now that you wanted to be able to withdraw $1,000 at the end of year one and $1,000 at the end of year two. And you wanted to know what amount of money you would have to put in the bank today in order to be able to do that. So to solve that problem, what do? Well, to solve that problem, essentially what we do is we calculate the present value of $1,000 a year from today and add to it the present value of $1,000 2 years from today. And so you can see what I'm doing in this equation is I'm taking 1,000 and I'm dividing it by 1.1, which is the present value of $1,000 a year from today. And I'm adding to it $1,000 divided by 1.1 squared, which is the present value of $1,000 2 years from today. And of course, not surprisingly, the answer is really the sum of the two examples that we just did, right? $909.09 is the present value of $1,000 a year from today. $826.45 is the present value of $1,000 2 years from today. So if you wanted to be able to withdraw $1,000 at the end of year one and $1,000 at the end of year two, you're simply adding those two calculations together and you're getting $1,735.54. What's key here is that even though when you look at that equation, you see the 1,000 written twice, you'll notice that I didn't take the first 1,000 and add it to the second 1,000 and try to operate on the number 2,000. And the reason I didn't do that is because even though those numbers look the same, they're not the same. And the reason they're not the same is because they're coming at different points in time. As I said, money has a time dimension. And so what I have to do in order to be able to calculate the present value is I have to first convert those into like terms. And the way I'm doing that is calculating the present value of each. So I'm calculating the present value of $1,000 a year from today and calculating the present value of $1,000 2 years from today. And once I know those present values, I can add them up because now they're stated at the same point in time. They are in present value terms, and then I can add them together. And that's why I don't add the $1,000 to the other $1,000 and try to do something with $2,000 because, again, money has a time dimension, and those two $1,000, even though they look the same, are fundamentally different. You probably wouldn't be surprised that if I took that $1,735.54 and put it in the bank for a year at the rate of 10% a year and withdrew $1,000 at the end of that first year, I would have $909.09 left in the bank. And then, of course, that would grow at 10%. And at the end of the second year, I would be able to withdraw the second $1,000, and there would be nothing left in the bank account. So this is just another example, and here the cash flows are varying. And so the question here basically is, what amount of money would you have to put in the bank today to allow you to withdraw $1,000 at the end of year one, $1,500 at the end of year two, and $2,000 at the end of year three? And this calculation is very much like the calculation we just did. And you can see what I'm doing here is I'm calculating the present value of the $1,000 a year from today by taking 1,000 and dividing it by 1.1. And to that, I'm adding the present value of $1,500 2 years from today by taking the $1,500 and dividing it by 1.1 squared. And to that, I'm adding the present value of $2,000 3 years from today by taking the $2,000 and dividing it by 1.1 to the third. So let's use a spreadsheet to calculate the present value of the example we just did, where we had a cash flow of $1,000 in the first year, $1,500 in the second year, and $2,000 in the third year. One way in which we could do this would be to calculate the present value of each of these cash flows. So in this case, we could take C2 and we could divide it by 1.1, because remember the discount rate in this example is 10%. And when we do that, we get $909.09. Then we're going to take the year 2 cash flow, and because it's the second year's cash flow, we're going to divide it by 1.1 squared. To calculate 1.1 squared, you put 1.1 in, and then you hit the caret. The caret is usually above the 6 on most keyboards. And then you put squared, and then that gives us the present value of that $1,500. And then the third year's cash flow is $2,000. And in order to calculate the present value of that, we're going to take the $2,000 and we're going to divide it by 1.1, now raised to the third power. Again, we have to hit the caret sign and then the third, and that's going to give us the present value of that flow. So now you've calculated the present value of each of the flows. So now to calculate the net present value of the 3 flows, we can just sum up the present value of each of the flows for years 1, 2, and 3. So to do that, we would just take the sum of, in this case, C3 to E3. And when we do that, we find out that the present value of the sum of those 3 cash flows is $3651.39. Now, there's another way to do that that's a shortcut, and that is to use the NPV function in Excel. So in this case, what we're going to type in is equals the NPV, and then the first argument that goes in the brackets is the discount rate, which in our case is 10%. And then you put a comma, and then you tell it the cash flows that you're discounting, which in this case are the 1,000, the 1,500, and the 2,000. So we would put in C2 to E2 to calculate that, and you see that the answer is the same, $3651.39. Now, up until this point, we've assumed that the interest rate on the bank account stays the same every year. And so we've just been talking about an R, and we've been assuming that the R stays the same through time. We can allow the interest rate to vary through time. But of course, if we do that, then we need to denote the fact that the interest rate for the first period is different than the interest rate for the second period, etc. And so the R now is going to have a subscript, which is going to refer to what period it relates to. So to calculate the present value when the interest rate varies through time, you take that F sub n, but rather than dividing by 1 plus R raised to the nth power as we did before, we now have to multiply the product of all the 1 plus R's together because the R's are different. So in the denominator now, again, instead of having 1 plus R to the nth power, we're going to have the product of 1 plus R1 times 1 plus R2 times 1 plus R3, etc. And so we can certainly allow for the interest rate to vary through time and still calculate a present value. So a quick example of that is, suppose you wanted to know what amount of money you have to put in the bank today to receive $1,000 2 years from today if the interest rate for year 1 is going to be 5% and the interest rate for year 2 is 15%. Well, to calculate that present value, you simply take 1,000 and you're going to divide it by 1.05 times 1.15. And the present value of that $1,000 would be $828.16.